a lot of what we do in neuroscience just focuses on the patient. And even that's probably an overstatement. It's really focused on the person's brain. So we don't think about that the brain's sitting in this person's body, the person's in this environment, the person has to talk to their loved ones, they have to interact with them, and so on and so forth. And it's like, well, if we took that model and thought about how do we take them out of the MRI facility and put them into having dinner with their loved ones, how do we actually study that in a way that's useful?
I'm John Foxe, Director of the Monte Institute for Neuroscience at the University of Rochester, and I'm absolutely delighted to welcome you to another episode of Neuroscience Perspectives. We've taken the podcast on the road to the Society for Neuroscience conference here in lovely, beautiful, sunny Chicago, and I'm thrilled to be joined by Dr. Randy McIntosh, Professor and Director of the Institute for Neuroscience and Neurotechnology at Simon Fraser University, one of Canada's preeminent academic institutions in Burnaby and Vancouver, Canada. He is also one of the founders of the Virtual Brain, an open source neuroscience platform that simulates the human brain and offers insight into how it works and how disorders like stroke, epilepsy, or neurodegenerative diseases impact its function. Randy, thank you for taking the time to come to join us today.
Happy to be here.
Let's dive into your research, but we'll come back to the computational stuff.
Sure.
But you're really interested in the development of the brain, really across the lifespan, and the sort of functional architecture of the brain. Where does that even come from? How did you decide to study this?
Well, that's a long story. I think the motivation really came from my foray initially when I was a postdoc, was doing some work on aging at NIH. And then when I was in Toronto, I was in a geriatric research facility called Baycrest, and there obviously the focus is on aging. It occurred to me, and it's not terribly surprising, that a lot of what happens to you when you get older is influenced what happened to you when you're younger. Anybody who's an athlete knows that if you got a busted knee when you're 20, you try and go skiing when you're 50, of course. It's like, my knee's sore, what's going on?
Yeah, right.
But certainly it's going to happen with the brain as well. So a lot of the approaches that one uses to understand that trajectory requires you to really have that sort of lifespan perspective. The challenge, of course, is that we really don't have data sets that cover that whole span. It's usually longitudinal studies typically are short, relatively speaking. So we had to find a way to kind of pull these data together. That's kind of the motivation behind doing aging and development, but then also trying to find a computational platform like Virtual Brain that allows you to sort of stitch these things together to make sense of it all.
Now, so this idea of sort of building a computational representation of a biological structure in silico, in a computer, where does that come from? Why would, like, tell the lay viewer out there why you would expect to be able to really model a human brain in a computer?
Yeah, I mean, it's not like we're trying to build a completely accurate representation of the brain. Right. That would be, otherwise we just build another brain.
Right.
What we're trying to do is understand what are the critical pieces that we can simulate that allow us to understand something important about it. I think the great analogy is something like, for example, flight simulators, where the whole aeronautics industry really had a huge boon when they improved their ability to simulate the consequences of certain design considerations for wings, for example, things of that sort. We can do something similar in the brain. So, we know that the areas are connected in a certain way. Does that have any relevance? If we change the connections and then try and simulate the activity that comes from that, does that look anything different in terms of what we see in real data sets? And you can go back and forth between them and say, if I model the critical features that I think are important for capturing dementia, for example, for capturing the evolution of language, for instance, what are those critical features? And I can test my hypotheses in the simulation itself. And the nice thing in the simulation is that you can do the experiments without having to actually pay for scans and so on and so forth. So it's a very efficient way to test your speculations and then try and incorporate the empirical data to give that validation.
Right.
The same way that you test wing designs and come up with a small set of candidates for wings that actually work and say, well, this one's the one I'm going to put onto this particular plane. And it's great because that way you can avoid having to actually test it and have the planes crashing, which you don't want to have happen, of course. So.
And all the work and effort that goes into performing human experimentation too. But is it one of these cases then where you can make some predictions from the virtual brain and then take it back into the field and say, does this actually happen in reality?
Precisely. I mean, there are some papers recently, not from my group necessarily, but one in development looking at the change, for example, of the balance of excitation and inhibition, which is a big thing in the brain, and how that evolves as we develop. And the model shows that there are certain things that should happen.
Right.
It's never been really shown, but those people went back and started doing some pharmacological experiments to show that, in fact, that's actually what we see empirically. So it's a great way of
validating the model.
Validating and testing and generating hypotheses for them as well.
Yeah. You know, it's interesting because in the field, right, there are folks that come to neuroscience from a computational background, a math background, and people who come to it from biology and pharmacology. And then there's a huge group of people who come to it from the cognitive sciences, right? They want to understand the brain. And many of those people, and I'm going to paint in a very broad stroke here, might be a little mathophobic. They came through the, interest from a psychology perspective and that. Would you go so far as to say that really there's no way forward in understanding the brain without having computational models, or is that too extreme?
I don't think...
I'm not trying to get you in trouble with all the psychologists.
No. I mean, my PhD is in psychology, so I come from that lineage. And I had those battles a lot. Certainly, like my when I was in Toronto, the courses I taught were mainly multivariate stats. In a psychology department. Right. So, half the class just absolutely hated me for how dare you put up equations. So I do think it's important to have a computational perspective. And it's important to realize that these computational models are great tools.
Right.
I don't think it's fair to expect all of the psychologists to learn dynamical systems theory and be able to derive the equations. But it is worthwhile to be open to what they show and to at least be able to have a conversation about them.
Right. At an intuitive level.
Yeah. And what that means, though, is that it's on the other side, the people who are the maths that are doing this, the applied mathematicians, the physicists, and so on, have to learn how to converse with the psychologist and make analogies or just show the equations in a way that's tractable so that they can have a conversation and then build the models jointly, for example.
Yeah, maybe even take that one step further. In the end of the day, right, our duty is to the people who pay the taxes to pay for the... So we need to be able to communicate this
for sure
to folks who aren't even in the field in a way that's understandable.
And you typically find that way of trying to communicate actually works really well for communicating to your colleagues as well.
Yeah.
Because it's not going down the lowest common denominator, but it's actually trying to make it tractable. And that exercise, that capacity is one that needs to be developed better in science.
Right. Yeah. I mean, I'm just thinking, like, you were certainly one of the pioneers. I'm not the person who really introduced structural equation modeling to what we do and that, and brought a lot of very good mathematical tools into the space. Right now we're in the middle of this AI revolution. It's as if AI showed up a couple of years ago, and yet I think if people in our field, we've been talking about these same mathematical procedures for 20-25 years. Are we at a discontinuity now? Did something happen 2 years ago, or is it just that it's finally emerged into the public sphere?
I think it's become easier to use the tools, and there's now a critical corpus of students. Critical number of students and scientists that are using these tools that are interested in applying it to the brain. Historically, it was interesting when I was in Toronto again that a lot of people who were developing these technologies, the algorithms for in AI, in machine learning, and so on, they did it a lot of times without thinking about the brain, without actually talking to someone who's actually doing the wet science. Right. So for them, it didn't really matter if that's how the brain did it. This learns face recognition really well. That's all they really cared about. But now I think there's that linkage that's been formed, and that's really what I think changed things, is that all of a sudden the gates open. Now we've got people going back and forth who are really facile in the computer science underlying AI, and people who are willing to take that step to apply it to their own data sets. There is, of course, and you probably know this as well as I do, that there's an assumption it's almost going to be a panacea for us.
Yeah.
And I think it's important to make sure that the realistic aspects of AI and machine learning are conveyed to people who think it's going to solve all the problems.
Right.
And that's where the problems come in, I think, is that overpromise, underdeliver kind of thing.
Yeah, exactly. Yeah. It's very interesting just to think, the dialogue, the narrative in the media about AI is so extreme now. And
unfortunate.
Yeah, and yet again, these mechanisms, convolution nets, all this stuff, it's really been around for decades in the neurosciences, trying to solve the problems that we think about every day.
Yeah.
And again, as you say, there's a real risk of expecting too much too quickly from.
Yeah. It's going to be an evolution. There's no question that almost all techniques do that. There is, depending on how far you're removed from the actual work done in ML and AI, is we need to be careful of not putting too much of a spin in either direction on that.
Right.
And that's where that tempering the enthusiasm, but kind of saying this is a great tool because it can do things that we could not do 20 years ago, but it's not going to solve your problem. It's not going to write your thesis. It's not going to solve your problem for you. You have to actually still think about what's going on.
Right. You and I had a conversation about this over the last few weeks. Thinking of the traditional way in which experimentation is done in human beings. We put them in an isolated, electrically shielded booth, or we have them doing something in a magnet, and they're highly unnatural. And we do it for control, right? So that we can really turn the dials in a very specific way in an experiment and control everything as best we can. But you've really started to think about getting out into the environment and measuring people in the real world doing what it is they do actually in reality. Yeah. Tell us a little bit about that and where your thinking is going.
Yeah, the motivation for that really came from getting back to my my years in Toronto. When you're, and you probably know this as well, when you're in a hospital facility and you kind of see what people are actually faced with when they're faced with different kinds of neurological aspects, stroke, dementia, and so on and so forth. Right. So there's them, and then there's the families, and then there's the extended family, and all having to deal with the challenges that are around that. A lot of what we do in neuroscience just focuses on the patient, and even that's probably an overstatement. It's really focused on the person's brain. So we don't think about that the brain's sitting in this person's body, the person's in this environment, the person has to talk to their loved ones, they have to interact with them, and so on and so forth. And it's like, well, if we took that model and thought about how do we take them out of the MRI facility and put them into having dinner with their loved ones, how do we actually study that in a way that's useful? Right. There's all this thing about collaborative cognition that's been out for quite a while, where all of a sudden the person, when they're with their families, seems to do better than if they're doing the regular cognitive assessment. You go, like, they shouldn't be able to do that, and all of a sudden they're remembering things. Right. And that's the kind of thing that's kind of puzzling, right? Because we don't have a way of studying that because we want to do it in a scanner. Right. But what if we did it in the person's kitchen or went to their community? And that was the motivation. And I didn't get a lot of traction, primarily because it was just there's a lot of other things going on. In BC, and especially in Simon Fraser University, there is this notion that the university is part of the community. And if that's true, if we really aspire to be part of the community, let's bring the community in. Let's work with them to start designing our studies. So I said, well, let's put our money where our mouths are and try and build a platform that we can take out into the different communities in and around Vancouver, take it into the interior BC, and talk to the communities about what they think is important for brain health, for brain resilience. What do they think are the most pressing issues? Work with them on trying to design some studies, have wearable devices that can measure not just brain, but body, and get those integrated in ways that we can now model with AI and virtual brain, but also use the communities as our collaborators. And I think that's going to really push the neuroscience in a direction that we need to go. Because it does integrate the person in the environment and the environmental issues that we deal with as well. But it also then allows the community to feel like they're actually part of that enterprise. And that's the important thing for me. Yeah, fantastic. And then we're sort of at this historical nexus to where the sensors, high bandwidth, easy deployable, cheap sensors are now available to us. And I mean, I think neuroscience has always been very good at adopting these technologies. So the ability is there now. Maybe that wasn't there 20 years ago, where everything was heavy and lugubrious and difficult, and we didn't have the bandwidth or the computing power. Yeah. And now you can you have it in your back pocket also,
Yeah,
essentially,
yeah.
really.
I love what you just said about the listening to the community at Rochester. Rochester is actually the home of what they call the biopsychosocial model of medicine, and this was the thought that you stopped thinking about a person as the disease that they walked through the door with, but as a person that was embedded in a family and a community and a culture and a medical history.
Yeah.
And so I think you've literally restated that very beautifully.
Yeah.
And we're in a position now to really measure the biopsychosocial context in which somebody lives.
Right. Yeah. And it's a complicated problem. I use the word complicated in the sense of getting back to some more discussion earlier about the maths underlying these things, that it's going to be an enormous challenge to find a way to integrate these data in the way that can be used. Because you think about, again, when we're talking about brain, we can measure neurons, we can measure populations of neurons, we can make multi-scale models, at least putatively. But now we're talking about a brain that's in a body. So we have these interactions between the visceral and metabolomics, the motor system and how the motor system interacts. And that becomes another level of modeling that we really have to kind of think about how to do well.
Extraordinary complexity, but the essence of actually being a healthy human being, all that interactivity in the other systems. And I suppose another challenge will be doing it equitably. And making sure that we get it to people who are in less technologically rich parts of the country and so
Definitely,
on. This is certainly a big consideration for folks, for example, with disabilities, movement disabilities, who can't come to the mothership, to the main university to get an MRI scan and that.
Yeah.
So there's real hope there that these sort of mobile technologies that you can push out into the community might have much greater reach than our current model.
I'm hoping so. Yeah, I mean, and again, it's also like the communities, like the Indigenous communities, First Nations communities, are obviously skeptical of these kinds of things. But I think there's a great opportunity there to work with them as partners on these things, to really understand their perspective on things. And there's some of the conversations I've had have been extremely illuminating, to really get a perspective that. And it's almost that the perspective they bring is that perspective that the person is part of this broader community, broader environment. Right. So if we have a way of actually incorporating that into how we do our science, that could really make a big difference, not just to us, but also to them.
Fantastic. Let's talk a bit about Randy McIntosh. Let's talk about the 5-year-old Randy McIntosh.
Okay.
So what were you like growing up? Where does the passion for science come from? I think I saw a story about you and your brother coming up with experiments and being just very inquisitive young men.
He was motivated by Evel Knievel.
Evel Knievel, that's it. That's what I saw.
Evel Knievel was a motorcycle daredevil who used to jump over incredible things. And one of the ones was the Snake River Canyon, which was, I don't remember when exactly it was, and he had a motorcycle that was basically a rocket. Yeah. So my brother and I tried to recreate that, and ended up putting my brother in a box and then setting it on fire. Unfortunately, we got him out of there before it got too bad. But
that's unbelievable.
Trying to build a rocket.
My brother and our version of that was to get the Evel Knievel Action Man. We didn't go any further than that. That's wonderful.
Should have prototyped it first, I guess.
There you go. So you almost set your brother on fire. That's how it started.
Yeah. I think he's forgiven me. I think he's forgiven me, right?
Yeah.
But so I started reading quite early. My mom says I was around 4 when I started reading encyclopedias, and I was just, this thirst for knowledge was always there. What I was interested in was quite diverse, everything from dinosaurs to climate to like different languages to history and so on. So the science has always been something that's really been driven. It's in this, I guess, an innate curiosity that was always there. And it never really changed. Even in the high school days when I was doing the rebellious things, there was still a scientist that was there. And certainly when I transitioned to university, there was a brief moment where I thought I wanted to be a lawyer. A very brief moment. After my first year pre-law, I was like, that's not a good idea. So I just stayed with science after that, and ended up being neuroscience. It was partly from some work in high school, but also partly from taking some classes in my hometown in Lethbridge, where it was really sort of inspired by the classes I had with people like Rob Sutherland and Ian Wishaw in particular.
So again and again, we hear of people who come in contact with very specific individuals who really just float their boat, get the intellectual juices running.
Yeah. And there were extreme. Like Rob was a new faculty at that point in time, so he was extremely interactive as well, because you could see the enthusiasm for what he was trying to do. And it's that enthusiasm for that path of discovery that really kind of grabbed me. It's like, wow, I could really see myself doing this.
And then you did your original undergraduate university up in Canada in Calgary, and then headed down to Texas for your PhD. And what brought you to Texas?
It was really the person I wanted to work with. So in Calgary, I started working with a technology called autoradiographic 2-deoxyglucose, which is basically a predecessor of a lot of the imaging stuff that we're doing now in humans, but I was doing that with rats. And there was a guy in Texas named Francisco Gonzalez Lima, who was using this method 2DG to make it easier to say in a behavioral sense. So when it was first used, it was kind of like what happens if to glucose metabolism if we give an animal ketamine, if we give it a stroke. But there were very few people doing what happens if an animal learns, for example, that an auditory stimulus is an aversive signal, classical conditioning kind of thing. And he was doing that. And I was like, I want to do that. So I sent him a letter, handwritten letter. And I got a letter back about 2 weeks later saying, come on down. So at that point he was at Texas A&M University, which is at the medical school there. And then a couple of years later, he got a position in Austin.
And you moved to Austin with him.
University of Texas at Austin, which was
pretty good. A good place to land for you, I happen to know, because of your passion and love for music, right? So music's another big component of
definitely. Yeah, it was one of these.
I can't tell you the number of people who've sat in that spot. Music is highly, highly overrepresented in the neurosciences or in the sciences. I think it's amazing.
It's interesting because I don't know if people think about it as a separate thing. I mean, certainly the process of creating music is different than analyzing data and thinking about the brain. But I don't know that they're different enough so that they're considered almost separate activities.
Right.
That a lot of, and I mean, we can test this, of course, a lot of the processes, the underlying biological process should be similar. It could be very much the case that a lot of the fluidity in terms of the mental processes could be similar as well. And this could be why music actually has such an appeal for people who are thinking about high thoughts, like either whether they be scientists or whether they be other people who are also in that creative genre that use these other things to continue to engage broader networks for their own enjoyment, but also potentially to also help think through problems.
I had somebody say to me one time, one of the things that she got out of music was that in the sciences and what we do, that there's a tremendous delayed gratification component to it. You start something today and you'll be very lucky if you see something useful or something that'll give you a little bit of a buzz for 2 or 3 years and often longer.
Right.
And she went home and she played some music and the product was right there. And that was something that she needed to tie
This is very true. This is very true. There's a gratification you get from playing music or even listening to music that's harder to get from getting your paper accepted in nature.
It's a long game. It's a long game. Yeah. Tell us, with your trainees, and I often ask this question. If given the gestalt, the zeitgeist in 2024 for a youngster coming through graduate school, do you have pearls of wisdom, advice about the world that they're entering into in the sciences? Would you do it again today if you had it to do over?
Oh yeah, no question.
Yeah.
As I said, I mean, science is deeply ingrained in who I am. So I don't think about my career choice as being a job. And that was something that I really found peculiar in talking to some of my other colleagues who treated science as a job.
Yeah.
And this is true for other professions. Whether it be art, you could think about other professions, medical doctor, for example, that you don't shut things off at 5 o'clock. And I think that's one of the things in science that it's going to sound smug and maybe a little bit elitist, but it's really, don't go into science if it's not a passion.
Yeah.
Don't think about it as like this. My job is to be a scientist because it doesn't stop at 5 o'clock on Friday.
Right.
Some of my insights come to me on Sunday mornings, unfortunately.
Yeah.
So it's like, I got to write that down. So I'm up at 4 o'clock in the morning on a Sunday trying to get this thing written down. And that's the way, musicians do that as well, right?
Yeah,
Musicians
of course,
get inspiration, or artists do the same kind of thing. And I think that's the attraction of being in this field. And it's, for me, I feel blessed that I actually get to do this.
Yeah.
I'm kind of stunned sometimes that I get paid to do this. Wow.
Yeah.
And that's, I think, one of the things that people going through the system now really have to think about is this something that really I think of as a passion, or is it something I'm doing just because that's what you do?
Yeah.
So going through bachelor's, going through your PhD, going through your postdoc, if you're just doing this because those are the steps, that's probably the wrong reason for doing it. Yeah. And stop at some point and think about, is that really what I want to do? I've been quite deliberate with my students to have those conversations a number of times, and be very frank with them. I'm not going to think less highly of you if you decide I want to go in industry, for example.
Right.
Because that's a good choice, and maybe it's actually what you want to do, and maybe be successful there. Try it.
Yeah.
Why
exactly,
not? There's no penalty, really. You may take a pay cut. Actually, most people going to industry get a pay raise.
Yeah, the pay raise.
But it's really allowing that opportunity to explore where they want to go and supporting them for that. And that's my job, is to really support their journey so that they're making the decision when they finish their PhD that they're going to be doing something that they're going to be passionate about when they're 60 or 70 years old as well.
Right. No off switch. It's, in the end of the day, it's a living, breathing thing. It's part and parcel of your very being to be, on the whole time. And I appreciate that too, that it's not a job, it's a privilege to get paid to do it.
For sure. Yeah. Like I when we moved to Vancouver, we have a place now on Vancouver Island as well, which is a great retreat. But when I go there, it's not like I shut everything off. It's a different perspective.
Yeah.
No question. But it's not like I...
But that's an important point of being a scientist too, right? Which is, it's one thing to be in the lab all the time and doing experiments. But the quiet time and the thoughtful time is where a lot of the work gets done. It might, and that's the part maybe that doesn't feel like work, where you're out on your bike and... Well,
the virtual brain history actually came not because Victor Yersin and I were sitting in a lab. We were sitting in a pub having a conversation about that, and all of a sudden inspiration came from that, right? And he and I do a lot of running together. So when we are on runs, we have these great conversations that are kind of meandering, and all of a sudden, we should stop and record this.
Yeah.
So,
So you could have been talking about the football game, or you're talking about this. It's just
right. Yeah. For sure.
Superb. Randy, thanks so much for taking the
Pleasure.
time
I enjoyed
with us.
it.
It's really great to have you here. Looking forward to seeing your work.
Yeah, thank you.
For years to come.
Cheers. Take care.